Hello everyone, I'm excited to present our work titled Towards Precise Scaling Laws for Video Diffusion Transformers. In this talk, I will share how we explore scaling behaviors in video diffusion models and what insights we have gained to improve both efficiency and generation quality. First of all, we believe it's crucial to establish a scaling law for video generation models, which cause huge compute budget and train a model. We aim to answer an important question. Given a fixed video transformer architecture and a compute budget, how can we predict the optimal model size along with its expected performance and optimal hyperparameters, especially for batch size and learn rate? However, there are three key challenges in answering this question. The first challenge is that private work rarely focuses on the role of hyperparameters in scaling laws. In our study, we revisit this issue and we argue that the choice of hyperparameters has a significant impact on the final performance. If hyperparameters are chosen empirical, the scaling behavior can become very noisy and unreliable. As shown in the figure, even under the same model size, different combinations of batch size and learn rate can result in very different final losses with same compute budget. In the figure, the red point in the plot shows that the lowest loss under the optimal hyperparameter settings. All the gray points are from suboptimal hyperparameter choices, which lead to worse performance. So the first problem we need to solve is that how do we identify the optimal hyperparameters so that we always land on the red points rather than the noisy gray ones? This is essential for fitting precise and reliable scaling curves. Secondly, using fixed suboptimal hyperparameters can impair the accuracy of extrapolation results. As shown in the bottom left figure, we illustrate this issue by comparing two approaches to estimating the optimal model size under a fixed compute budget, both using the same set of fixed hyperparameters of batch size and learn rate. The blue curve shows that the result of directly running experiments across different model sizes and picking the best performing in one under the compute limit. The red curve, on the other hand, it diverges by first fitting the loss as a function of model size and training tokens, and then extrapolating from that fitted curve to predict the optimal model size. As we can see, the red and blue lines diverge significantly. This gap is caused by noisy loss value from suboptimal hyperparameters. Thirdly, using suboptimal hyperparameters introduces bias, usually an overestimation. As shown in the bottom right figure, the blue curve with suboptimal settings estimates a larger optimal model size than the red curve with the optimal settings. Under the same compute, but larger doesn't mean better. Only optimal hyperparameters can fully use the compute and reach the lowest loss. So suboptimal setting not only hurt performance, but also mislead model size selections. To address the issue, we propose building a scaling law for hyperparameters. First, we focus on the optimal batch size. Here we provide a high-level result. Details are in the papers. The optimal batch size balances per step gain and total number of training steps to maximize overall training improvement. It depends on two factors: T, the total number of training tokens, and N, the model size. Secondly, we build a scaling law for optimal learn rate. Just like batch size, the best learn rate balances per step improvement and number of effective updates. It also depends on total number of training tokens T and model size N. Thirdly, we propose a performance scaling law. We make two key assumptions. First, as model size N approaches to infinity, the minimum achievable loss depends on the training data entropy and noise. Similarly, as training tokens T approach to infinity, it depends on model size N. Second, with infinite compute, as both model size and training tokens approach infinity, the loss of diffusion video transformers approaches to training data entropy L loss infinity. Next, we present our main fitting results. First, we show the result of predicting optimal hypermeters. As shown in figure, we predict hypermeters match the lowest validation loss found via research, which confirms the accuracy of our method. Then, we predict the optimal model size under a fixed compute bucket using optimal hypermeters. We compare two approaches. One is direct search through experiments, and the other is extrapolating from our fitted loss curves to find the model size and minimize loss. As shown, the two results are highly consistent. This confirms both importance of using optimal hypermeters and the accuracy of our fitted skin loss. Finally, we show the fitted loss surface over model size and training tokens. Under the optimal hypermeter settings, our fitted loss curve matches the actual data points very well. We also perform extrapolation, predicting the loss for 0.7 billion and 1 billion model under different compute levels. The predictions closely match the observed results, confirming the accuracy of our loss model. That's all that concludes our brief overview of this work. If you have any questions, feel free to reach out. We'll be happy to discuss further. Thanks for your attention. Thank you.